this webinar by wishing you good morning or afternoon or evening. Welcome to this CSDMS webinar series. I'm not sure if everybody is familiar with CSDMS, so I'm going to very briefly say a few words about CSDMS. CSDMS stands for Community Service Dynamic Modeling System. And we're basically representing a group of people that are, in the broadest term, kind of exploring the Earth surface and how it evolves. And I say in the broadest term because it also includes the oceans and the coast, so it's not only terrestrial. And we're doing that by applying and developing and promoting numerical models. CSDMS is organizing a webinar series. Our speaker today, Anders Penuela, is the last of the spring series we have. And I think we don't have a summer series, but we will be back in the fall. So keep an eye out for that. Like I said, today's speaker is Anders Penuela. Anders is a postdoc scholar at the Universidad de Cordoba in Spain. He's actually he has a Marie Curie postdoctoral fellowship, which is pretty prestigious and offered by the European Union. And his research topic involve hydrological modeling, reservoir modeling, and soil erosion modeling. So, some model expert. And in the presentation today, Anders will focus more on demystifying modeling. So trying to make models less of a black box, lower the barrier for use. Trying to elevate collaboration with, for example, decision makers. I'm super enthusiastic about it because we're trying to reach something similar with CSDMS. So with that, please hold your questions towards the end of Anders' presentation. And if you could post them in the chat, that would be great, but we can also open the microphone. So with that, Anders, please go ahead.
Thank you, Albert, for the introduction. I don't have much more to say about myself. I'm a modeler, and this project focuses on soil erosion modeling and hydrological modeling. The philosophy behind this presentation is something. In some example, I will focus on that direction on soil erosion modeling, but I think that it can be applied in any other field. So I hope it's useful for anyone using model in general. So why demystifying modeling and how? This is something that I would like to answer during the presentation, but just briefly. One of the main objectives or the initial objective of this project is to make modeling more accessible and transparent. Because I believe that in that way we can somehow democratize modeling, so more people can participate, more people with different backgrounds, different views. So somehow we can also make models more robust with the participation of different people with different backgrounds, with different opinions. I believe that we can make modeling more robust and also more exploratory. And why? Because I still think that we have to try to increase also the trust on model results to make better decisions, to make more or better informed decisions. As I said, sometimes I'm gonna focus on soil erosion modeling on agriculture. So just to show you an example, I would like to ask this question: how do farmers, in my case, decision makers, increase their understanding of the land, of the system? So first of all, by observing the land, the system, under different conditions, climate conditions, under different seasons, and the different land management practices, and also through interaction. By interacting with the land, they can test, evaluate, for example, how good or how bad is one land management practice. So they somehow interact with the land and see the response of the system. This long-term experience or interaction creates a high level of trust in personal observation and past decisions. With models, we can, let's say, accelerate this long-term process of interaction, of building trust in our experience or in our interaction with our system. And we, for example, we can allow for rapid exploration of the effect of long-term processes, in my case, soil erosion, and under countless scenarios and conditions. For example, let's imagine that we have a soil erosion problem in our field, and we would like to evaluate how the system will react, what would be the effect of changing, for example, the land management practices. For example, we stop using the tillage, the soil, maybe we grow some vegetation between our trees. This is an olive orchard, actually in the south of Spain. Or maybe we can even decide to change the crop. So we can evaluate and compare these different scenarios in a much more rapid way. So we can actually make better or more informed decisions. But what is the problem? The problem is that models are complex to use and to understand, and especially for people without the technical knowledge. What elements of modeling are easier to grasp for someone without the technical knowledge? So in modeling, we have the inputs. Usually they are not so hard to understand for people without the technical knowledge. For example, rainfall time series of, I don't know, daily rainfall. Or maybe the representation of the topography of a catchment with a digital elevation model. Or maybe also the context and goals of our model. For example, we would like to mitigate the impacts of soil loss in our agriculture catchment, or maybe when we want to optimize the irrigation systems, or maybe optimize the reservoir operation. Those are concepts, both the inputs and the context and goals, which are, let's say, tangible. They are familiar to us, so they are not so difficult to understand. What about the outputs of a model? Sometimes the outputs are not that also difficult to understand. For example, this is a map of the soil loss across catchment, so we can see clearly what are the areas and the risk of soil erosion, while we can also see other areas which are not under risk. True that some of the model outputs are not that easy to understand, but usually we modelers, also researchers, we put some time, we put some effort to make our results clear, not only for ourselves, but also for the others, for other researchers, and also sometimes for the public or for the decision makers. What elements are trickier or usually left to modeling experts? The model itself. Not only the model code, but also the model equation that we are using to simulate the different processes. So all the science behind these models. Why? One of the reasons, I believe, is that there is one myth. Before, I was talking during the presentation that models are complex to use and to understand, but maybe they are not so hard to use and to understand. But there is a myth. Models are inherently hard to use and to understand. And part of that is due to us, modelers and researchers. Sometimes we focus more on communicating results than on demystifying the models themselves. So for users without the necessary technical knowledge, the model may look more like a black box. They may see some inputs getting into the model, and then they don't know what is going on in the model, but then they see some outputs getting out. this creates a gap between researchers, modeling experts, and decision makers. Usually, a decision maker probably has a good knowledge of the system that we are trying to simulate, while we don't have so much information or so much knowledge about this system. So while there is a gap, sometimes there are interaction. This interaction between researchers, modeling experts, and decision makers usually is quite limited. So maybe we as decision makers, let's say farmers, about some information that we need to use in our model, to fit our model to use for the simulation. Then because we have a good modeling knowledge, we run our system, maybe previously we calibrate our model, and we share that info, the model results, with the decision makers, which usually don't have, or they have a very limited knowledge of modeling. And this creates a lack of trust. Because as I said, decision makers or people without the technical knowledge see the model like a black box. They don't see what is going on inside of the model. And not only that, but usually in modeling, there is a lack of transparency about the uncertainty. In my opinion, that also contributed to this lack of trust in model results, and as a consequence, in a poor adoption in decision making of models and model results. So in the end, what happens is that the decision makers, they usually rely more on their past experience to make decisions than on the model outputs. And also, I believe that this limits innovation. For example, adaptation for climate change, to optimize your land management practices, to mitigate soil loss. And this is actually quite common, at least in my field in agriculture, this is quite common. Farmers usually make decisions based on their experience, or sometimes even what their parents or grandparents told them to do. So the question now is like, okay, but how can we, or someone without the necessary technical knowledge, can understand and trust a model? And to answer that question, I'm gonna make another question. Did you learn to ride a bike by reading a manual? I'm gonna assume that most of us learn to ride a bike by doing, so basically through interaction. And this is the basis of the toolbox that I'm developing in this project, the impact erosion toolbox, which is a hydrological and soil erosion modeling, which is meant to be, first of all, interactive, but also modular, playful, and accessible and transparent. Okay. Let's keep this in mind. Making the models accessible and transparent are not that easy. Okay. The target audience of this toolbox, the impact erosion toolbox, are students, researchers, and also decision makers. On that, this toolbox has two main features, or two, let's say, key innovation. One is the use of educational Jupyter notebooks with interactive visualization for creating a more fluent conversation between the user and the model. But I didn't talk about it, but I was just focusing on non-technical users. But what about us? What about technical users? Even for technical users, models can be hard to access. And I've been in that place many times. Sometimes it's really hard to access, to understand, to run a model that was not developed by you, developed by someone else. And there are several reasons for that. One, for example, could be the lack of coding skills. Maybe my skills in coding are not good enough to understand the code because it's written in a very sophisticated way. Maybe the model is not very user-friendly. Maybe I don't know the language, the programming language that was used in this model. I'm more into Python, MATLAB. I don't know much about R, but I know nothing about C++, Fortran. So sometimes I have also that problem. Something also very common that I find very quite usually in models developed, or that I found, for example, on the internet, is that they are poorly commented. There is also a lack of explanation, not only about the code, but the science behind. What is the modeling process, which the explanation of each of the modeling steps. Sometimes even the code or the data is not provided. And also, many times I have problems when installing, trying to install a model because of the installation requirements, maybe because there is incompatibilities between libraries, maybe because it was designed for Linux, but I use Windows. So again, even for us, for technical use, the models can be also hard to access. And again, sometimes we can see models as a black box. One usual solution for that, to make models more accessible, let's say easier to use, is the use of model interfaces. But in my opinion, when you have an open code, like when you have access to the code, you are more like in front of a Django, and you have to try to explore that Django to understand the model. While an API is more like a highway crossing that Django, and it takes you from the input to the output, but in between, you don't see much. So somehow, while you make the model easier to use or more user-friendly, I think that we lose in model transparency and flexibility. So in the end, do we make more models more accessible with APIs? And actually, what do we mean by model accessibility? And especially, what do we mean by model accessibility to a wide range of users? Maybe some users, for them, accessibility is about how easy it is to use the model. But others may believe that accessibility is more about how easy it is to modify and adapt. Is it free, open source? Is the data and code really well available? Is the code easy to read? Is it the model easy to reproduce, to share, and to understand, and then to trust? And I believe that if you want to make models accessible, you should check not only one, but maybe several of these conditions, okay? And as I said, making models accessible and transparent, or let's say easy to use and transparent, is not that easy, because when we are pushing in one direction, probably we are losing on the other one. So when we use APIs, we gain in user friendliness, but then we hide details, we make the model less reproducible, less flexible. And when we use open models, we remove this user friendliness to make it more exposed, to show the details, to make it more reproducible, flexible, and somehow more trustworthy. So can we get to a balance, like easy to use and transparent at the same time? As I said, that is not easy, but this is what we try in this project. And for that, we are using Jupyter notebooks, but we take it a bit further, or let's say one step above. So Jupyter notebook, for those who don't know about what is a Jupyter notebook, is a document where we integrate everything that we need in a model. First of all, text with explanations about the modeling, the modeling process, about the equation behind the model, about the system that we are simulating. We can also use images, diagrams, even videos. And then we can combine, or we should combine it with the code of the model. So we have access. The code is transparent. We have access to the code. And actually, we can run it inside of the notebook. In Impact notebooks, we try to make this explanation more educational. So we start from the basics of modeling, from the basic to more sophisticated techniques in modeling. Also, the code that we are using, in this case, Python, we make an easier to read Python code. And I will explain a bit more about that. And then we also integrate interactive figures, not static, but interactive. What I mean by more educational Jupyter notebooks, we try in the explanation to, as I said, to try to explain the modeling from the basics, and also trying to use, for example, analogies. So we can try to make people without the technical knowledge to understand some concepts, technical concepts, by making an analogy to something that is more familiar to them. For example, here, a digital elevation model with a landscape made of Lego pieces. With this feature of the notebooks, we try to remove two of the limitations. For example, when the model is poorly commented, or when there is a lack of explanation. Let's go to the second one, easy to read Python code. What do I mean by that? Usually, for example, in this presentation, I use in English because we use a common language. In science, we use English as the common language to communicate between different people from different countries. While in modeling, we have many languages. I know Python, I know MATLAB, but I don't know anything about JavaScript, HTML. So what can we do? Like, can we have a common language? I believe so. And one common language that we have is mathematics. It doesn't matter where you are, mathematics are the same everywhere. So we can try to make coding more math-like style coding. I'm going to show you an example to explain that concept of math-like coding. We have a community hydrograph that we want to convert into a normal hydrograph, so daily hydrograph. Not only in one place, but in many places, no, for different dates. So the basic operation will be to go day by date and subtract the cumulative volume from the day before to the current day that we are estimating. And do this for all the dates and all the different locations. Okay. In Python, we can do something like that. That is one option. We can create a function that is going to do two loops. One will be for each of the location, and the other one, the nested one, will be for each of the dates, and we'll do this operation, as I said, subtracting the cumulative volume from the previous day. So something that I believe someone with limited coding skills and some knowledge of mathematics will be able to understand. A software engineer will tell me probably that this way of coding is very inefficient because using loops and nested loops takes much longer than, for example, using NumPy libraries. For example, that function called roll that is shifting one row lower, so we can do this whole operation in one line much faster. And actually, I tested the speed and it was actually 50 times faster. But at the same time, we are reducing the code readability, and especially for people with limited coding skills. Maybe they don't know that function. They don't even know about how this function works. So the question now is like, okay, can we keep this math-like style, I believe this code readability, but also making the code efficient? And actually we have one tool, one very useful tool, which is the just-in-time compilers like Numba, which basically actually, the basic idea of Numba is that it speed up the code, and actually speed up especially code with loops inside. So we can create a code that is still readable and efficient at the same time. So it allows for computationally expensive tasks like ensemble simulation, multi-objective optimization, and still using a math-like programming language, easy to read and write by users with limited coding skills. Okay, and now with this feature, we can try to remove these two limitations, the lack of coding skills and the and that the code is not provided. Okay. Then let's go for the third one, interactive figures. Okay, what are interactive figures? Interactive figures are reactive figures plus intuitive elements like sliders. So in that way, we can interact with our model just by playing with the slider, with the values of the parameters of the model. And we can see instantaneously the change or the reaction of the model and also the response of our system. This, first of all, make the model, the notebooks, more user-friendly. It removes the need to deal with the code. So people who are not into coding at all, and they don't have any knowledge about coding, they can still play with the model, and they can still interact with the model parameters. That facilitates the exploration of the model behavior and the results. For example, here we can see how the model uncertainty also changes. We can interact with the sensitivity. We can see what parameters are more influenced and how these change when we change the range of variability. And basically, we use a library called HiPy widgets and Matplotlib. Not only that, but this is something also that I use in my lectures, but I can explain some technical concept of modeling with interactivity. So for example, I can explain the concept of soil erodibility, which is tightly or is quite well related to the features of the soil and in particular the soil texture. So how a soil with more or less silt, clay, or organic matter will have different soil erodibility, also the structure, the permeability of my soil. I can also explain concepts like sensitivity analysis and uncertainty analysis, or some others more like filling weather data. A common problem with data that I have found, I have had many times in my life, is that I have gaps in my weather data. So let's do some interactive figures to explain how we can fill that data with some statistical distribution, like the normal distribution to fit temperature data. And not only that, but we can also compare different methods of solution. For example, here, what I would like to do is to interpolate especially some soil loss estimates across a catchment, and I can use 3 different methods of spatial interpolation and compare them instantaneously, okay? And again, with this third feature, we can remove the limitation of a model which is not user-friendly or a model that is using an unknown language to me, because I can still use the model. I can try to understand the model with this interactivity without the need to deal with the code. And actually, this is not new. This interactivity with models is widely used in machine learning, and this is called interactive machine learning. And why in machine learning? Because basically machine learning models are black boxes. So even model developers, they don't really, or they don't fully understand their model. So they have to interact with the model to make sure that the results make sense, or what they expect from the model is what they see in the results. Basically, in machine learning, this interactivity is introducing the man in the loop, not only when the human is in interact with the model before and after the process of modeling, but during the process. And it creates what the main objective is to increase the transparency and the robustness and user confidence of this type of models. At the same time, from what I understand, you also reduce a bit the model accuracy, but by building trust in the model, you make the model more suitable for real-world application. Also, this is not new because we also apply this interactivity in another toolbox, but in this case, in reservoir operation optimization. I evaluated how good is this interactivity in explaining technical concepts in reservoir operation, simulation, and optimization, only with students, but we saw a very positive feedback from them. So with this interactive visualization, we facilitate this user-model interaction and also the exploration of model results. So we get a better understanding of both the model, but also the system that we are simulating. So with a better understanding of the model, hopefully we can enhance the trustworthiness of the model results. And by a better understanding of the simulated system, we can also make better decisions. So in the end, we try to bridge this gap. First of all, by increasing our modeling understanding or the modeling knowledge of decision makers and also of researchers. Okay. And also by increasing the system knowledge of researchers and again, also decision makers. Okay, so we create a more educational and exploratory modeling approach. This toolbox, as I said, the audience is quite wide, so it can be suitable for people who have some knowledge in soil erosion, in my case, but in your field, maybe on the topic, but they have some knowledge in the topic that we are trying to study with the model and with the model code, for example, researchers, but also maybe users who have some knowledge about hydrology, soil erosion, but not into coding. They are not interested in the code. For example, practitioners, or they don't even have any knowledge about hydrology, soil erosion, not into coding, for example, students. Okay. So we can also hope to create a better interaction, first of all, between the research and the professional community, but also to increase the understanding and also to make modeling more accessible to students who actually are the future researchers and professionals. You can find this toolbox on this website. It's divided in 3 sections. Well, the toolbox is under construction. I'm uploading gradually some of these notebooks. The first section is the start. So it's basic concept of modeling, first steps in modeling, in this case, hydrological modeling and soil erosion modeling. Then the test is basically the evaluation of our model, calibration, also sampling optimization. We can go to the field to acquire some data, but we can acquire that data in a more optimal way. The interpolation of this data, and also do sensitivity and uncertainty analysis. And the exploration, the explore section, which is basically the exploration and the comparison evaluation of different possible scenarios, for example, future scenarios of climate change and land use change, the impact, the effectiveness of mitigation strategies, and again, also sensitivity and uncertainty analysis. And just to finish the slides, I would like to say that the model is available on GitHub, on the website that I also show you in the link on the previous slide. But actually, it can also be run on the cloud. So you don't need to install Python, Anaconda, Jupyter Notebook. You just need a web browser. And this is possible thanks to GitHub and plus Binder. Okay, and I will show you, after I finish the slide, I will show you how. So with this, also, we can remove the last limitation that I put in this diagram. So the installation requirements. So I'm done now with the slides. I will be happy to have any collaboration. This toolbox is supposed to be very modular, so I'm using some hydrological model or soil erosion model, but I will be open to get contribution for other researchers. I just wanted briefly, before I finish this presentation, to show you the website, which is in here, I think. Okay, so this is the website. I have to say that you had your repository on GitHub. You can create a free website. This one, okay, I'm not a web developer, so it's quite basic, but it still is quite useful. I can explain the 3 sections that I talked about before. I can show you some links, for example, directly to the GitHub repository. I can guide you through the installation if you want to install the package locally. I can go, for example, to the first section and click directly to run the notebook online. For example, the first one that we have in the start section is field climate data gaps using probability distribution. If I click on that link, that will take me directly to Binder. And hopefully sometimes it takes longer, but in a few seconds, we will see the notebook. And we will be able to run the notebook online, just with a web browser. You don't need anything else, okay? And I can start running my code. I will see my inputs. Here, as I said, I try to explain all the basics of, in this case, filling weather data, what kind of distribution we are using. I can introduce some interactivity. What about changing the mean value? What about the standard deviation? How does it look like? Also can make some question, so I can try to push the user to improve the fitting between the data that you have available and also the one that you are using to fill. So it's somehow I also try to make the notebooks a bit more playful, okay? Here I have more examples. I can get out from here. I can go to the second one, which is filling the sinks of digital elevation model. Again, usually it takes only a few seconds. So you can imagine you can share those notebooks with your boss, with your colleagues, and they don't need to do anything else. They just can start directly playing with the notebook. As I said, I try to use analogies to explain some of the concepts. As I said, this website is created on GitHub because my toolbox is on the GitHub repository. You can download it and use it locally on your computer as well. And I just wanted to show you how useful this binder. I don't know how many of you know binder, but if I, for example, copy the link of my GitHub repository on binder, this is just what I do. I do launch and it fails. Let me try again. I have to say that this service, okay, it's a free service, so sometimes it's not very reliable. I don't know why it's not working now, but in theory, when you launch it, it will open again a Jupyter Lab window, where you will be able to go through your GitHub repository and load your notebooks online. And actually, to make sure that that is going to work, that the libraries, there is no conflict between libraries when you run it on the cloud. By putting this file inside of your GitHub repository and making sure that you have the necessary libraries, sometimes you can also specify what are the versions that you need. Then when you will run it on Binder, you will be able, or anyone will be able to run it as it will be running the notebook on my computer as the model developer, okay? And I think that's it. Thank you for your attention. I'm happy to answer any question.
Wonderful, Anders. Super nice presentation.
Cheers.
I enjoyed it. Let's see. So if somebody has a question, you can either put it in the chat. And actually, let me do a step back. I put a link of the GitHub repo that Anders just showed, so you can click on it and get to the page that Anders showed, and you can play with it. But if you have any questions, you can put it either in the chat or you can raise your hand, and I should have the capability to unmute you, and you can ask the question yourself. So while you are pondering on your question, oh, and I see Greg has a question. So Greg, go ahead.
Yeah, thanks, Andreas, for that great presentation. I have a bunch of questions, I guess. So So one is sort of a technical question. You showed these interactive examples using IPy widgets and matplotlib. Have you experimented with models that take a while to run so that you can't just change a setting and the model runs in a fraction of a second and reproduces results, but it's gradually going? This is something I've tried and so far failed to do, to have a user able to sort of change a setting while a model is actually running and displaying in real time what the output is.
Yeah. Actually, I'm kind of lucky because in solid ocean modeling, I mean, there are different models, but the most widely used model is very simple. It's an empirical model, but yeah, most of people are using it because it's very easy to understand and to run. So I don't have that kind of problem with soil, with this type of soil erosion model. But as you get or start to use more sophisticated models, this interactivity start to get quite laggy, and the experience is kind of different. To me, it's quite important, like when you do this interactivity, that the reaction is instantaneous, because then you develop your conversation with the model is much more fluent. So one possible solution, first of all, is, as I said, use, for example, just-in-time compilers that speed up your code. In my case, even using loops, I can make the code much faster. Another option, when you are trying, for example, when I deal with the students, maybe instead of using a very sophisticated model or a lot of data, I use a smaller study area. I use somehow a simplification of the model so I can keep this interactivity. The same way, for example, with sensitivity analysis or uncertainty analysis, we have usually the same problem. With sensitivity analysis, if the model is it has very high computational requirements, then it's really hard. And in our case, in this toolbox, I wanted to make even sensitivity analysis more interactive, because I think that it makes you understand the model behavior much better. So again, using more sophisticated models, more data, then the experience is quite different. But I think that still there are solutions for that. Maybe you can do simplification of the models to show what is the model behavior for non-technical users. And then when you will make some decision, then use the full version of your model. I know that in sensitivity analysis also there is not like a one solution for that. So sometimes it's a bit of a compromise. Yeah.
Sure.
Can I ask a question as well? Anders, you indicated that that you can make your code more, I guess, readable or understandable when you're using mathematical coding, right? To change the written lines basically more in mathematical functions. By doing so, do you think there's less need or absolutely no need anymore to include comments, to include documentation, or do you think it doesn't take away from including comments in your code as well? That still should be a good practice to have that too.
Probably I forgot to mention that, but apart from in the notebook, you have the explanation in Markdown, like you have different cells, but also inside of the cells, I encourage people also to comment their code. Maybe not line by line, but the main section, I think it's really important to comment them. And I believe that from that point, you have your explanation, your comment on the code, then there is no need for more documentation, external documentation. You will have everything in one document in the notebook, and you will be hopefully able to understand the whole model step by step. But yeah.
Okay, thank you. Are there other questions? And again, you can paste them in the chat and I can read them out, or Greg, go ahead.
I don't want to monopolize the questioning, but since there was a moment of silence, I figured I'd jump in. So I'm curious about what your experience is using this with stakeholders like farmers. How have you introduced this to farmers? Have you done, for example, facilitated workshops where you or others are guiding people through an exercise or something like that?
Not yet. As I said, my main interaction is with now for the moment with the students, but the last part of my project, we are gonna try to have more interaction with farmers. One thing that I would like, first of all, to try to show, to prove that static modeling, maybe not self-explanatory as more dynamic or interactive modeling. Maybe I will start from the simple and maybe I could do then in the next month, because the last, as I said, the last 6 months, starting in June, we will start this interaction with decision makers, stakeholders. And then maybe we can develop a workshop going through different notebooks and see if they can understand the process of soil erosion modeling. Maybe they can understand also better the problem of soil erosion, which is usually something that you don't see on the field because it's a long-term process. But if you can show that in a model, maybe they can also realize how much impact soil erosion is having in their fields, but in the long term. But yeah, hopefully in the next month I will be able to answer your question, but for the moment I can.
I'll be really interested in the answer. Our colleague Moira Zellner has been working for a while in participatory modeling and has developed a web platform that's more like the API example that you mentioned, so that the model. So it's the CSDMS project. We use notebooks and cloud-hosted Jupyter notebooks a lot for the research community. But she's doing it for stakeholders. In her case, things like urban flooding and things like that. Let's see, where was I going with this? So I'd be interested to see how your experiences compare or contrast with hers in terms of like what people find useful. Seems like the interactivity element is really important. I guess this is sort of leading to another question, which is the idea of I love the idea of demystifying models. On the other hand, I can imagine that you have to make trade-offs. I've just finished teaching a semester of a numerical modeling course to geology graduate students. And these are smart, focused, hardworking students, but it still took, a full semester of instruction just to introduce some fundamental concepts of numerical methods and numerical programming and, let alone more advanced concepts like error analysis or uncertainty propagation and things like that. So do you have a feeling for what kinds of things, if you can't communicate everything that you need to understand a particular model, what are the things that are most important to try to get across to demystify?
I think that probably demystifying modeling is more like a gradual process. You start from the basics and then you try with more complex or sophisticated concepts. With my students, I try to do that. Like I try to, with very simple, basic concepts of modeling, and then I start to build up in complexity. And I think that if they can understand the first concept, then it's much easier to go for example, for concept of what is sensitivity analysis, what is uncertainty analysis, and as you said, maybe uncertainty propagation. It's true that in my case I couldn't go that far away because for example, I'm now teaching some Erasmus students. They have a very different backgrounds. So their background because it's so diverse, I had to start from the very basics and then start to build up. So by the end of the course, maybe I didn't get to that point, or maybe, okay, go for very, very complex concept of soil erosion modeling. So I don't know if there is a limit, there is a roof, maybe, but I believe that, yeah, if they have motivation, or you can motivate them to use this interactivity, I think that they can understand some of these physical concepts, some of these concepts, even without the need to understand the question behind, just with this interaction. But again, maybe next year also we'll be able to answer that question as well.
Thank you, Anders. I think I want to point out that Greg earlier talked about the things that Moira has been using or developing, and it's called Fora. I put a link in the chat for those that might be interested in that. And it's similar, but it's not towards notebooks. It's more like it's a web-based platform where actually groups of people can interact with a model, set up a simulation, and then run the simulation, make changes, and run it again. And so it's less interactive in the what you have shown, but it's still quite, because you have to wait till the simulation is done and then you can start a new simulation. But one of her findings, I think, and I'm sure I'm doing short in explaining this, but I think what she accomplishes the most is, I think, the interactions between different decision makers, make that happen around a model, and make people think more about solutions. In her case, it's about or she uses as an example flooding in cities, and what are the ways to minimize the impact of flooding, and so people can implement different tools. You can put different pavers that make the soil more permeable, so there's less runoff. But everything comes with a cost, so it's a cost balance kind of that city planners have to make. But she says in the end, it's not about the simulation itself, but understanding, where to put pavers and have a discussion around that. So anyway, that's.
I will be very interested to know more about the project. So
yeah, I can. I will send you some links afterwards.
And actually, talking about that, the decision-making process, we did some before. When I did my previous postdoc was about reservoir operation modeling, and it's true that it's not only about simulation, as you said, it's also about the decision maker. What are their preference when they take decision? Because in the end, there is no like a one optimal decision, but there are many of them. We were, for example, representing Pareto from multi-objective decision making, where they have to choose, okay, what do you like? What preference you have in operation? Save water, save energy, and that process of interaction also, I think that helps them to see these trade-offs between, okay, because in the end, as I said, there is never an optimal solution. There is always, when you're pushing one way, you are losing on the other way.
Yeah.
So yeah, I will be really, really interested on reading.
Yeah. I will share more of her project with you after this. I see Craig has one other question, and maybe more general. What are the alternatives for Binder?
That's something that I would like to know.
Yeah.
No, actually, yeah, we'll be happy to get some suggestions about that, because to me, Binder is a very good solution, but at the same time, is you could see during the presentation, not very reliable sometimes. But just sharing a link and making people interact with the notebooks, and that's it. To me, is it's a very good solution. Maybe there is also Google I don't remember now the name exactly. I tried a different way with Google, but I couldn't have my data on the cloud, so I had some problems, and I ended up using GitHub binder anyways. But yes, if any of the people attending, they can tell me, or any other alternative, will be very happy. Good.
Yeah, I think the one thing we might have learned over this last half year or a little bit longer is maybe that, you know, being dependent on one platform might not be super healthy. So yes, I agree. If there are better alternatives, and anyone in the audience, please share with us. And yeah, like Greg indicates here in the comments, we have set up our own Jupyter notebook, but that's, you know, then you need to have some financial resources to be able to do so. So we were lucky that NSF sponsored this for us. Are there any other questions? If there are no other questions from the audience, we're coming up to the hour. So, Andreas, thank you very much for your presentation. I will reach out to you in a couple of hours from now. Thank you everybody for attending. This is recorded, like I think Lynn indicated earlier, so we will put it on the CSDMS portal. If if your colleagues are interested, please share the webinar link on the CSDMS portal, and people can see Anders' presentation as well. So with that, thank you very much. Anders, have a good rest of your evening.
You too.
And thank you everybody for attending.
Thank you. Bye-bye.